Hello, and welcome to APICS Extra Live, Spare Parts Optimization for Complex Networks with Dr. Vitaly Volovoy and Dr. Dave Peterson of the Logistics Management Institute, better known as LMI. My name is Jennifer Strelli, Associate Editor at APICS. Before we begin, I'd like to run through a few details. At the end of the presentation, we'll save time for a question and answer session. If you look at the right toolbar on your screen, you'll see a questions box. To ask your question at any time during the presentation, simply type it in the box and click Send. Should you experience any technical difficulties during today's broadcast, please call GoToWebinar Tech Support at 1-805-617-7000. Again, that's 1-805-617-7000. This presentation is being recorded and will be available at apics.org/extralive early next week. And now it's my pleasure to introduce our speakers for today. Dr. Vitaly Volovoy is an independent consultant at LMI. His principal fields of expertise are system safety, risk and reliability, and analytics for complex engineering systems. Dr. Dave Peterson is a senior consultant at LMI. He specializes in readiness-based sparing. Dave also works with federal agencies and commercial firms on supply chain and operational analytics projects. Vitaly and Dave, along with Margaret S. Wise, co-authored the APICS Magazine July-August 2016 article, Amplified Availability, which is available in print, online, and through the APICS Magazine tablet app. Everyone, please give a warm welcome to Vitaly and Dave. Vitaly, you may begin.
Thank you, Jennifer, for this wonderful introduction. What you see on your screen is the quote from the article that Jennifer referred to in July-August issue of APICS. And that probably summarizes what we're trying to say here in today's webcast. When we're looking at the effectiveness of operation and support activities from a complex network perspective. So we're trying to look for a big picture here. And I must say that there are two speakers and we will be switching back and forth between myself and Dave. And the way you can kind of tell us apart is that you can hear good Russian accent here on my side, so that you know that if you hear Russian accent, that's me, otherwise it's Dave. If we go to the next slide, I will, this is the agenda for our talk, and we'll try to fit the talk around 45 minutes or so. So we'll introduce complex networks first. We'll look at the importance of system-wide performance viewpoint that I mentioned in the introduction. We discuss the importance of leveraging analytics for better performance. And when we speak about analytics, we'll talk about the importance of big data, but also some important differences compared to the way the big data is used in other domains such as advertisement and similar things which do not have structured processes, and we discussed the differences briefly. Then we talk about contribution of sparing models in this respect, and then we go back to the big picture and provide an example of measuring system-wide performance and why it is important. And in the end, we'll field the questions. We can go to the next slide. So what is a complex network? We define that as a multiple system that deliver common functionality and share common operation support. So in this context, even though what you see on the right here, you see on the top picture of a group of freight aircraft. You can see in the middle Schiphol Airport Tesla parking lot. And on the bottom you can see the Chinese fast trains. Either one of those, all of these three examples represent something that actually moves, but it's kind of accidental. The functionality doesn't have to be moving. You can have, let's say, power stations or something that does not connect to the network itself. Here we see the connectivity that we will be discussing is coming from the economies of scale, pooling resources in terms of operation, that is providing service to the customer and relying on the fact that you have the economy of scale there, and also on the side of the maintenance support we have some pooling resources there as well. So there's connectivity both on the operational side and on the maintenance side, even if you don't have the connection in terms of the connectivity based on the functionality itself, such as, let's say, internet or the pipelines. So in any case, we will move to the, we will use the coupled networks and the system of systems interchangeably. So the next issue that I want to discuss is the explaining why networks are becoming more complex. And we have three kind of contributing factors here. On the one hand, we see that there's an evolution toward greater efficiency and capability that drives the complexity, and the nodes themselves, when we're looking at an individual system that comprise the network, become smarter. So those nodes have ability to operate more intelligently, and Tesla would be a good example of that, or moving forward with the Google cars and things of that nature. We also now can coordinate a large number of nodes, so we can take advantage of the scale effect. And there's some drawbacks potentially when we're looking at the disturbance to these large systems as well, so they need to be taken into account and have sufficient redundancy to ensure reliable delivery of the service. So, but on the top of that, we have more sophisticated coordination of operation and maintenance that might be, time dependent, depending on the time of the day, bring more or fewer systems online. And this is, again, this is enabled by the smarter behavior of individual nodes. Going to the next slide. Dave?
Okay. Thank you, Vitaly, and good afternoon to our attendees. As Vitaly noted, sophisticated systems require equally sophisticated sustainment networks and practices. For example, SpaceX's Falcon 9 rocket and Dragon capsule, which is shown on the diagram or the picture on the right, the first stage of that rocket and the capsule are actually designed to be reusable. So SpaceX's sustainment policies to support that reusability really need to understand how those systems are being used and how they're going to fail. Now, remanufacturing space systems is not new. In fact, NASA and some commercial aerospace firms did have experience with remanufacturing spacecraft with the space shuttle in terms of the shuttle proper and the solid rocket boosters. But as operational policies become smarter, so do sustainment policies. And as an example here, SpaceX actually recovers the first stage of that rocket. They've recovered it on land, but actually more often they've recovered it on a barge floating out in the ocean. And likewise, they recovered their capsules via parachute into the ocean. So, those type of operational policies pose a significant challenge to supply chain managers. For example, these are fairly complex systems, and either one of them by themselves have thousands of distinct parts. And even though the fleet, say, of the rockets in this case is not that great, when you take the combination of the number of parts and the fleet size, it literally can approach the hundreds of thousands or millions of parts that supply chain managers have to wrestle with. But another challenge that they face is controlling life cycle costs. And life cycle costs can be thought of is kind of the sum of 4 different cost categories, where each of these categories is associated with a sequential but overlapping phase of the system's life cycle. And really, when you talk about life cycle costs, the question that comes to mind is, well, what is it going to cost us to not only acquire a system, but then to operate that system and its associated support network? And the issue is systems incur different costs throughout their life cycle, and probably the best way to think about this is maybe a little bit closer to home analogy, and think about when you go about buying a personal automobile. And if you're like most people, I bet the first thing that you do is you start researching car buying guides, seeing what the experts have to say on it, looking at the specifications of the vehicles and so forth. And then you probably move to going to dealerships and test driving the vehicles. And at some point, you finally decide, well, this is a set of capabilities I need, the specs that I'm looking for in a car, and you make a buying decision. And at that point, you move from research and development into kind of the acquisition phase. And, in terms of buying a car, at acquisition, you may have to be thinking about things like, well, am I going to have a trade-in? Am I going to pay cash for it? Am I going to have to take a loan and spread the payments out over time? And those same type of budgetary decisions are faced with even systems that have larger fleet sizes. Well, as soon as you buy or acquire that first system and start operating it, then you're going to move into what's called operations and support, or O&S. And going back to the automobile analogy, the things that you pay for kind of on a daily or your monthly or yearly basis, gas, oil, tires, routine and non-routine maintenance, even insurance, all those things get rolled up into the O&S costs. And we'll take a little bit closer look at other systems in the next slide, but it's the same idea for aircraft, vehicle fleets, maritime systems, and so forth. And then finally, at some point, as you're approaching the end of the useful life of the system or your vehicle, you're probably going to decide that you want to retire it, maybe get a replacement vehicle. And even in the retirement phase or the disposal phase, it's likely that you're not going to totally avoid costs. For example, if you're trading it in, you might want to spend a little bit of money to touch up some of those nicks and dings to make it look better. Or if you're going to hand your vehicle down to someone else in the family, you probably want to address a few of those nagging mechanical issues that you lived with, but you want to, give that person a better vehicle. So these are the 4 major cost categories over the life cycle of a system, whether that's your personal automobile or a larger fleet. But the point that's most relevant for the discussion today is that area in red, operations and support. And people who have studied this area say that typically 60 to 80% of the cost of owning and operating a system over its life cycle occurs in O&S. So let's take a little bit closer look at what O&S costs are. And remember, they're actually incurred from the initial deployment of your system through the end of its operations. And it actually can be a mixture of fixed and variable costs. So for example, if we look at the electrical grid schematic on the left-hand side, some O&S costs that might pertain here would be, say, personnel, the salaries of the technicians and the people who are running the system, the training costs to get them up to speed. Facilities, when you have this type of expensive equipment, it's very likely you're going to have specialized buildings, and you either construct them new or rent them out. And of course, as soon as you have facilities, at some point you're going to be incurring more maintenance and very likely taxes or insurance costs. And then there's the equipment and the operational technology. For example, this is a electrical grid where you have a gas turbine that's generating the electricity. It also has different series of transformers, not to mention the transmission lines and the towers. So of course, all that equipment also incurs a maintenance requirement. It may need periodic updates or inspections, and it may need overhauling occasionally. And that's where really the next category, supplies, is probably most relevant to the APICS audience, because as soon as you are starting to operate this equipment, you're going to begin kind of a wear and tear process, and at some point, some maintenance is going to be required, and that's where spare parts and supplies come into play. There's other cost categories too. For example, IT. In today's world, it's not just hardware, but also the software and the maintenance of the software and the information assurance and so forth. And finally, services, transportation services, engineering services, and so forth. So the operations and support portion of a system's life cycle can definitely be costly and complex. And the way that system managers often manage this complexity is by taking a network perspective. And on the left here is an example, a simple example of a reverse logistics supply chain. And it starts in the upper right-hand corner with a pool of spare assets. And these assets are deployed to the base and are used. And at some point during that process, a failure will occur, and they will then enter a retrograde to a higher level, a higher echelon, where a maintenance process will occur. And meanwhile, as soon as that broken part is evacuated from the base, and a replacement comes from the base spares pool. Now, as that broken part gets to a higher level of maintenance, it'll enter some sort of maintenance queue where it is actually disassembled, inspected, and a repairability decision is made. And if it is repairable, it'll enter the maintenance process, get fixed, reassembled, tested, and then re-enter the supply chain as a replacement serviceable spare, typically at that higher echelon. Unfortunately, sometimes the parts, their failures exceed repair capabilities, and then they are lost to the system, and they need to be replaced, and therefore create a new procurement. So ultimately then, the base, as its spares are whittled down, will launch a reorder back to the higher echelon of supply, and it will be replenished from there. So it's really just kind of a circuit here. And the key is that it's important to balance the process capacities across this network. And for an inventory manager, really the idea is you need an inventory of sufficient size that you can sustain a flow of assets through all these many different processes. It's almost an analogy might be at your home, if you're going to be watering the garden or your yard and you have a hose, and the question is, how high do you turn up the spigot so that you get enough water pressure so you can water the flower bed or the garden, but not yet wash away all the mulch or all the flowers. So it's kind of a balancing process. And let me go ahead and just kind of run this. This is actually a Vitalia will talk about it later. It's a small simulation that he did in a bridge Petri nets. But you can see here, as the assets flow through, while they're serviceable, they're green, and then as they fail, they turn to a yellow, and they flow through the repair process, and some which exceed repair turn to a darker orange color. And I don't know if you caught it, but partway through this, towards the end, actually there was asset starvation that occurred because the base spares ran out. Then there was no operating asset at the base location, which kind of brings me to the point about back to optimizing. And the idea is when you used to talk to people, they would have a very local perspective and they'd say, I'm going to optimize my particular process. But the problem with that is if you optimize any given location on the supply chain in isolation, what it typically does is just shift a bottleneck somewhere else into this flow. So really you have to take a more system perspective. The other aspect of this is optimizing assets to the wrong metric or optimizing assets using bad data can lead to other inventory problems, such as either inactive inventory or having a shortage of inventory and having back orders and an inoperable system. So at this point, I'm going to turn it back over to Vitaly, and he's going to talk a little bit more about the impact of big data on supply chains.
Thank you, Dave. So yes, indeed, the data, big data, is creating quite a lot of hype at the moment, and some people talk about zero marginal cost on the horizon for physical assets, effectively replicating the success of drastically reducing marginal cost in the digital world. If you think about, let's say, electronic book, once you created a book, creating extra copies doesn't cost you much. And some people think that something similar can be done in the physical world, and that's the kind of selling point of industrial internet, or internet of really important things, as GE refers to it. And maybe that's zero marginal cost is not quite there yet, but quoting a famous writer, there's something there, or paraphrasing rather. We definitely have this trend, and Dave referred to the pitfalls, potential pitfalls of local optimization and looking kind of at the problem in the stovepipe fashion. You can clearly see the trend of creating cradle to grave kind of support, reflecting what Dave described, the entire life cycle of a particular product. And they're supporting infrastructure that is created for sensing, collecting, and processing data from individual network nodes. And as an example, we can mention the Pivotal Cloud Foundry, GE Predix, and IBM Bluemix. But there are other people working on combining or merging potentially information technology with operational technology. And realistically, we hear some discussion about the futuristic world where there's zero marginal cost and all of these things are controlled together. But one of the first kind of immediate realistic use cases for this industrial internet or Internet of Things is actually sustainment. So if we go to the next slide, I want to briefly point out that when this discussion of big data is used, what the analytics comes to mind. And when people are talking about analytics in the current sense of the word that's used for selecting advertisement for you when you Google something, those models are effectively black boxes. So you have what you see on the left on this chart. You have some inputs and you have some outputs, and you're trying to figure out how the outputs relate to inputs. At the same time, using kind of blindly those methods, and those methods are nice because they're domain blind. They scale well, which Silicon Valley really likes. So you can create it once, and if the algorithms are nice, they can be applicable everywhere. But in engineering world, where we have the systems that are designed to follow certain processes that are engineered processes, we cannot avoid including that information into our models if we want to have good prescriptive and predictive analytics. And that leads to what's called Whitebox models. And what you see on the left, I'm sorry, on the right, you can see the Whitebox model when you have the inputs, but you also take explicitly into account, when you do your modeling, you take into account the fact that you know what the internal structure of your processes is. In particular for sustainment, you do need to go with the Whitebox models, and Dave will talk about it next.
Okay, well thanks, Vitaly. And this diagram is actually an example of how a Whitebox model coupled with big data can help enable effective sustainment. And on the left-hand side of this diagram is our system, if you will. In this case, think of it as maybe a fleet of snow plows. But I'd like to, I know that the APICS audience can extend beyond folks just operating vehicles or that. It could also be things like a set of industrial robots on an assembly line, or mechanized material handling equipment at a distribution center, or packaging equipment in a consumer packaged goods manufacturing plant. So think of the system as really just any large-scale type of complex system. But in this case, we'll just use the vehicles as our example. And as you're operating them, of course, accidents will happen and parts will break. And so, for example, in this case, let's say they're operating the snow plows and a brake lining or some sort of wheel failure occurs, and that part, the truck is sidelined and the part has to be removed from the truck. And hopefully there's a serviceable replacement for that part in their local field supply. Meanwhile, that broken part is going to be moved to a field maintenance activity, and someone's going to examine it and decide, is it really broken? And if so, can we fix it here? If they can fix it there, then they can return it to their local supply warehouse and put it on the shelf for the next time it's needed. If that part's failure, though, exceeds their local repair capability, then it gets evacuated typically to a higher echelon of maintenance, maybe a regional facility in this case. And again, at that point, the maintenance process begins and an evaluation is made. And if it can be repaired, they'll do so and then send it to typically a regional warehouse. Meanwhile, at that regional warehouse, they've hopefully had that part in stock and are sending it forward to replenish the shelves at the field supply. So again, it's this flow idea and keeping everything in balance. Now sometimes the parts are broken so badly, even the higher level maintenance cannot repair them, and so the parts are condemned and disposed of. And in that case, to keep the system in balance, a procurement order has to go to a manufacturer for a replacement part. Well, the question becomes then, how many repair parts do you need flowing through this network so that you can keep the snow plows running when they're needed? And readiness-based sparing is a proven analytical method to answer this type of repair part question. And you can think of readiness-based sparing as really having three main phases: an input, a process, and an output. And on the input side, there's three typical blocks of data or information that you need to run readiness-based sparing. And the first one is, can you describe your supply chain? In other words, is it a single echelon or is it a multi-echelon network? Do you have a centralized depot facility, or do you have multiple distribution centers? And how many bases do you have? How many operating locations are there for the equipment that you're supporting? So you have to be able to describe your supply network. Secondly, you have to be able to describe the utilization and timing for your system. And let me explain that. Utilization really is an expression of how intensely you're going to be operating that system. Is it something that you run 24/7? Is it something that you only run when there are snowfalls or having ice storms? You know, is it something that you measure its utilization in terms of flying hours or steaming hours? The other part of the utilization and timing is, you know, is this kind of a steady state process where the load on the operating system is even over time, or is it more dynamic and you have variability in how intensely you're using your systems? Because that will make a difference in your sparing approach. And then finally, you need to have item level data. And you know, you can probably think of this as akin to a repair bill of material, where you have a list of different parts, and each of these parts has different indicative data. For example, mean time between failure, unit price, percent of base repair, percent of depot repair, how long does it take them to repair, what's the procurement lead time, and so forth. So with these inputs, you're then able to come up with a prediction of demand for spare parts upon the system. And given that predicted demand, you can play out alternative sparing decisions against that demand and then measure their effectiveness, typically in terms of what we call expected back orders or long-run back orders. Once you have that information, then you can shift to the output side of this readiness-based sparing. And really, back orders are just the flip side of what we call system availability, meaning if you have no back orders against your particular system, then it is up and running, or what we call available. On the output side, you'll see the availability to cost curve. And on the x-axis is inventory investment, and on the y-axis is the system availability. And the red line represents really just a series of iterative inventory decisions. And any points along that line can be disaggregated into what we call a shopping list that tells you which parts to buy, how many of those parts to buy, and where to locate those parts. So let's take a quick look at a sample availability to cost curve. And again, remember the x-axis is inventory investment and the y-axis is system availability. And there's really two ways that inventory managers use this type of curve. And one would be, if they have an idea of what their inventory budget is, they can enter the curve from the x-axis, read up to the availability to cost curve, and then read across to the y-axis and see what type of projected system availability that investment will give them. Another way that they can use this curve is if they start with the y-axis on the availability they need, read across to the curve and then down, and it will tell you the corresponding amount of inventory investment needed to achieve that system availability. So while readiness-based sparing provides a great start to the sparing solution, we found that simulation is a natural complement to these analytical solutions, and Vitaly will go over the simulation approach next.
So the difficulty with the simulation is, of course, you have a complexity that you need to deal with. And we suggest that there should be 3 steps that kind of divide and conquer strategy that helps to deal with this complexity. The first step is using the big data approach to understand what individual elements of the sustainment processes are and what their properties are, how much delay you get on a particular location, and what the split is, whether you, let's say, knowing how many parts are actually being successfully repaired versus the one that you need to replace with new ones. The second part is what Dave just described, is understanding and optimizing the sparing based on individual parts behavior. And then finally simulation, that's what I will be talking about, of entire system and resulting in the network behavior and looking at the complex operational and maintenance interactions, such as changes of intraday patterns of supply and demand. And what you see on the bottom here is the example of a group of squadron of UAVs that are monitoring the fire. And there's some supporting equipment, including ground stations, that that ensure that these operations occur. And from the point of view of what Dave just discussed, we can have the availability of each individual aircraft, and we can also have availability of, let's say, ground stations, and we can spend money for the sparing of each of the systems. But what we really care is about the coverage. That is, we want to make sure that there's enough aircraft that can fly and monitor the fires at any given time. And that is what we're trying to model with the simulation. So when we go to the next slide, we will use a particular kind of simulation that we found very useful for us because it's called bridge Petri net. So this is a type of a discrete event simulation that is a kind of a balance between traditional discrete event simulations and fashionable nowadays agent-based models. So like agent-based models, these Petri nets provide the peer-to-peer interactions that are graphically modeled, so we can look at the non-hierarchical construction of the model and have this peer-to-peer local interactions. And I will show you how this is graphically modeled. Unlike ABM, you have few standard building blocks that leads to transparent and self-documenting models, so you can record the models and basically the assumptions of the model are present there, so you don't need to use computing languages to create levels. So it kind of reduces the barrier of entrance in terms of how much money you spend on creating models, how much money you spend on maintaining the models, and how much time it takes to get the input data for those models. And that provides a minimalistic representation of the causal processes, which is important because it bridges the gap between the traditional big data kind of models that effectively have one box and the million moving parts, a very detailed discrete event simulation or agent-based model that can have, as we discussed earlier, if you have 1,000 systems and each system has 1,000 different parts, you start talking about some serious models pretty fast. So let's go to the next slide. And here I'll show you a simple example of a model where we have 6 customers that are sometimes need cars and sometimes don't need the cars, and you can see how this actually, even though it's a simple simple model, but there's a relatively intricate behavior that's modeled here. In particular, you have these inhibitors and enablers. You see those curvy things right here, right? That's enabler that as we start the simulation, you'll see, and this is an inhibitor with the empty circle, you will see that they manage the interactions between the objects in the model. So you have the cars on the one hand and you have the people on the other. And basically the model just says we have 3 cars and those cars sometimes break. So if we start the simulation now, you can observe how there's the first customer comes in, but one of the cars breaks. So now you basically have a limit, so now you have to wait, and when another car breaks, it kind of pushes out the customer. So you can see that this model actually, even though it's simplistic, but it allows you to model fairly complex behavior here with the permutations. If you try to model these permutations manually, it would be quite a feat here. So importantly, note that there's a little square boxes, solid square boxes, and those square boxes allow you to monitor the, like the one showing here, and on the top, thank you, Dave, they allow you to collect statistics. So when you run what's called a Monte Carlo simulation, nowadays a Monte Carlo simulation becomes fashionable. It's even mentioned in the yesterday Wall Street Journal article. So you can collect statistics and you can have a rigorous statistical foundation for your decisions as a result. So now we move next to a little bit more elaborate model, and that is the model that showed a couple of slides prior of the group of UAVs. We have 4 UAVs and 2 ground stations, and here our modeling objective is to actually model the coverage as opposed to just availability of each individual let's say aircraft or individual ground station. And that is important because it might be that our targets for availability that Dave discussed for individual systems might be different for different parts of the system of systems. So we might have, for example, more stringent requirements for the line of sight ground stations because we have more redundancy for the aircraft, and we might not need to have as high availability of the parts because we might be able to afford to wait a little bit for parts for the aircraft. So let me start this. This is fairly long video, so I'll start that and explain how things are going. So one important thing here, as the aircraft starts, you see you need to have at least one line of sight operating, and that you have C enabler there that is required to make sure that the aircraft, now you can see that one of the line of sights is down, but another one is still up, so therefore you can still fly. But you can have a situation where 2 of the aircraft are down. Now the yellow aircraft here indicates that it needs scheduled maintenance. So when it gets to, you see it gets to the scheduled maintenance, it happens fairly fast, but you can see that this way you can track the need for scheduled maintenance as well. So far everything is going great, except that now we have the aircraft that turns red. It needs the maintenance. So it goes into the maintenance, and in this case we have parts available, so everything is nice, and the aircraft is repaired. It still takes some time to repair the aircraft. Now if you noticed, what also happens is that we're trying we broke down on the top, we have the orbiting and the request. Those 2 places, what they call, have the sensors, and we measure those combined statistics because both of them represent the actual coverage. The aircraft is there and it monitors the fires, and we can collect the statistics, and Dave will talk a little bit later what happens as a result. Now we're coming toward the end of the simulation, and you see this aircraft was a little bit less likely, so you see now it got into the logistic delay here, and that is basically the role of the supply chain, and this way it can get stuck there for quite some time, and we have the statistics that we got from the operational data that we can evaluate. So as a result, we have a relatively compact model, but it is showing you and enable you to model what happens with the entire system and how successful you are in achieving your objectives. So we go to the next slide, and I think Dave explained. Go ahead, Dave.
Okay. Thank you, Vitaly. Now, as Vitaly mentioned, with the coverage results from that UAV simulation, and you could get other performance measures like coverage for other scenarios, but the simulation basically allows you to move from a supply-oriented performance metric to something that's more operationally oriented. And that's what I think is the real benefit from this integrated modeling and simulation approach. For example, you can see on the left-hand side here, this is the previous availability, the cost curve that we looked at before. You know, it's a standard RBS grain space-sparing solution, and oftentimes an inventory manager will pick an investment point that's somewhere around the knee of the curve because that's one of your more efficient areas for investing on the inventory side. However, that's not necessarily tied closely enough with operations. And for example, running the simulation multiple times, as Vitaly had just walked you through, we generated this red line, which is coverage, and it's actually the coverage over the wildfire for the different levels of inventory investment. And what I think is important to note is that the coverage curve has a much different shape than the system availability. In fact, it's much flatter. So, depending on what performance metric is most relevant to your particular customer or your particular operation, the metric of choice can make a huge difference in the inventory investment that you want to make. So we're nearing the end of our allotted time, and Vitaly is just going to summarize with some highlights the benefits of integrating the analytical and simulation methods.
Yeah, so thank you, Dave. So to summarize here, we're trying to enable planners to translate the traditional RBA's goal of available systems into a performance-based measure that is more meaningful to operational activities. Rather than using some intermediate metrics, we're trying to track the metrics that really matters. Coverage, it might be the number of successful missions that we need to accomplish, and it might be any number of the final activities, and especially now when we are turning from the providing system, engineering system service rather than the product, it becomes the corresponding objectives might change, and so we can stay tuned to that. In the process, we capitalize on the one hand on big data technology. It's really important to have your plugged into the data and keep your models current. But at the same time, we feel it's very important to have the knowledge of structural process and supply chain as well, and not rely on black box models. So what we feel we have as a result a framework for adding complexities of the network to the model while trying to keep it nimble and flexible by using divide and conquer strategies. And I think it's important not to get bogged down. I've seen too many examples where people are trying to create humongous models, and they create it once and then they're collecting dust and never used. So we're trying to avoid it here, and we feel that that's realistic. And on the one hand, what we see here is that we have the opportunities with the infrastructure created by the Internet of Things to collect relevant data and use it. And at the same time, because now we're dealing with the services rather than product, the importance, the incentives of running your systems more effectively and managing the cradle-to-grave assets in a most efficient manner, that really provides more benefits than probably in the past. So that enables sustainment managers to balance the resources at their disposal to achieve desired performance outcomes rather than some intermediate metrics. Thank you.
Great. Thank you so much, Vitaly and Dave, for that very informational presentation. And now we save time for questions and answers. As a reminder, you can type your question in the questions box on your toolbar, and we will try to answer them for you. We'll now give you a couple minutes to send in your questions. Okay, our first question comes from Peter, and Peter asks, how long has the method readiness-based sparing been around?
Okay, that's a good question, and basically readiness-based sparing, or the, if you will, the basic idea behind it has been evolving probably since the 1950s, and it originated in more of a defense environment, but since then it has actually bled over into the commercial world. And it started out in the 1950s, where actually this idea of thinking about repairable items flowing through a pipeline started. and it was actually a Air Force project that George Danzig, who was a famous operations researcher, was working on. And then towards the late 1950s, the idea came up, instead of optimizing the inventory item by item, that they should evolve into a multi-item optimization, kind of the very genesis of a systems perspective. So they started computing using analytical techniques so that they could compute, if you will, spares levels for different items based on their contribution to a system level performance measure. And then by the mid-1960s, Craig Sherbrooke, who actually was a researcher here at LMI, he started out at RAND and then moved to LMI, he came up with a technique called metric, or the multi-echelon technique for recoverable item control. So they expanded from having this, if you will, multi-item optimization to they looked at multiple items being optimized across multiple echelons of a supply chain, so kind of the base depot relationship. And then in the 1970s, they shifted the inventory modeling from, if you will, minimizing back orders to more of the maximizing system availability. And then finally, in the 1980s, a gentleman by the name of Jack Muckstadt, who now teaches at Cornell, he expanded this approach to account for items that have an indentured bill of material. So they have, if you will, items that have parent-child relationships, because the net contribution of a parent item to the system's availability is much different than the contribution to system availability of that child. Since that time, this approach has been used in the commercial world in terms of aerospace. It's been used by NASA for the space shuttle and the space station, and it's also been used in for vehicle systems and for some rail systems.
Great, thanks, Dave. Our next question comes from Deb, and Deb asks, where does a supply chain manager start in attempts to understand how to change this type of analysis?
Okay. I can give a quick start on that, and then Vitaly can probably pick up. I think it kind of depends on what their primary responsibilities are, but if they're looking at just kind of the supply chain in general, to me, I think the idea is you have to understand things from a system perspective. And, if we can go back to, this slide, too often, people are involved on a kind of a day-to-day basis, wrestling with the problems of the day, and they're very localized problems, but these problems also have not only a local effect, but more of a systemic effect. So I think probably the first thing from a supply chain manager's perspective is to make sure that they understand really how their supply chain is operating and are able to kind of draw out this model, because to me it's the basis for everything else. How you want to design your inventory system, how you want to design, if you're going to use a simulation model, you need to have this level of understanding. I don't know, Vitaly, you want to jump in on anything there?
Yeah, I think I agree with what you just said, but I think it's also important to, as you mentioned, the system level perspective, and not to get bogged down in details and kind of look at the big impact of things, like looking at the overall picture that hopefully doesn't, basically of this resolution, what you have on the slide, maybe a little bit more detailed, and kind of just get the first cut first, and then you can drill into details and see what happens afterwards. But I think it also, now we are in transitional period where I mentioned Internet of Things, and depending where you are in terms of the kind of connection to that movement, but there are clearly very strong movement now in a lot of corporations happening where there's a push for the infrastructure related to the collecting the data and storing it in the cloud kind of like foundries and similar systems. And so the availability of the data that you have about the process also determines what kind of modeling you can do and what kind of analysis you can do.
Great, thanks both of you for the answers. I think we have time for one more question, and this one comes from Russ. And Russ wants to know how market and economic demands change differently with up and down parts demand compared with service parts usage.
I want to make sure that I understand what the question there is.
Russ, if you're on the line still, if you want to maybe give us some clarification, that might be a bit helpful.
Oh, if he's referring to whether it's a steady state or a dynamic type of operation, how does that affect demand?
Yeah, let me try that, Dave. I think that's a great question. The way I understand it, we're talking about the fact that you can have you're right, there's some dynamic effects, and depending on how successful, for example, you are, so if you're supporting your system all the time, you might, you have effectively closed loop between how well you're supporting your system and how much demand you have. So on the one hand, and we can look at the different time scales actually, because on the one hand, if you're successful, and we know, for example, Verizon was famously, they were providing this advertisements about the reliability of their systems, and that was a way for them to capture their market share. They were more expensive than other providers, but they were more reliable, and that was a way to capture market share. So you can look, that's kind of a larger time scale when you're looking at the situation where if you're successful in delivering a reliable performance, you capture more market share. But you can have a short-term impact that's probably more what the question was about, and that is depending on how successful you are in supporting your system, you demand changes as well, so you can actually smooth, you have more control over what you do, as opposed to, let's say, if your system breaks all the time and then you basically putting out the fires all the time, not the fires in the model that we are talking about, but more kind of in a symbolic sense, right? So the key is that this modeling, that's where the simulation is really helpful, because it can help you to capture those effects, and you can have those closed loops effects considered and taken into account, and you can, this way, you can provide, importantly, justification for improving things, and you effectively can build business cases and show that, you know, if we do this, this is how much better we will be, and this is kind of provides incentives to spend the money on some of the improvements, because obviously improvements usually require money, whether we're talking about this extra spares or some other type of investment. And but the key is that you can put hard numbers here if you do the simulation, and you have a better case with going to the people that have the purse.
Great, thank you. Well, that's all the questions we have time for today. At this point, I'd like to thank our speakers for their great presentation and all of you for joining us on today's webinar. If you have a few minutes on your way out, we'd appreciate if you take our brief survey to tell us what you liked about today's webinar and how we can improve the APICS webinar program. This concludes today's edition of APICS Extra Live. I hope you'll consider joining us for our next APICS Extra Live presentation on October 20th. Please visit apics.org/online events for more information. All content and materials included in this edition of APICS Extra Live are the property of APICS, Dr. Volovoy, and Dr. Peterson, and are protected by the United States and international copyright laws. All rights are reserved. And we'll leave that last slide up for a minute, because if you have any further questions that were not answered during our Q&A, you can reach out to Dave there, and that's dapeterson@lmi.org. Thank you everyone for joining us today. We hope to see you at a future webinar. Have a great rest of your day.